The pot contract is like a savings account for holders of DAI stablecoin. If you deposit DAI stablecoin into this contract, you'll earn interest. Now, you might have a brilliant idea of depositing a collateral, minting DAI, and then putting it into the pot contract. This way, you're earning free money, right? Well, actually, the savings rate on the pot contract is carefully set so that the fee that you'll have to pay on the borrowed DAI is greater than the fee that you will earn by depositing into the pot contract. In this video, let's rewrite the pot contract. I'll start off by copying the contract, and then inside my code editor, I'll open a file called pot.sol and then paste the code in here. Okay, let's start with the interface. So here it has an interface called VatLike. Let's rename this to ICDP engine. ICDP engine. Next, there are two functions called move and suck. The function move we already implemented inside the CDP engine. However, the function suck we have not implemented yet. I'm going to first go over to the interface for ICDP engine, and then we'll rename these two functions. So going back under interfaces, ICDP engine. So here is the function suck. I'm going to rename this function as mint. So going back, I'll paste this here, and then I'll do the same for the function move. Search for the function move. Okay, here it is. I'll copy this, and then I'll paste it here. So the function move, we renamed it as transfer coin. What it's going to do is transfer the coin from source to destination for the amount read. And the function suck, we're going to rename it as mint. Now, we have not implemented this function inside the CDP engine yet. We will implement this function in the next video. And what this function is going to do is it's going to mint an unbacked amount of DAI to coin destination for the amount read. Since this amount is unbacked, it also needs to account for the debt that it has created. And this is where this first input, debt destination, means. The coin will go to coin destination, and the debt will be allocated to debt destination. Okay, now that we have our ICDP engine interface, let's take a look at the pot contract. First, it has some code for authorization. We've already implemented this inside the library called auth. So going back, we'll just simply remove this and then import auth from one above lib auth.sol, and the pot contract will inherit from the auth contract. Okay, next we have the data pi and some other data that is used for the savings rate. We'll come back to this later. What I want to focus now is, notice we have a state variable called like, and it is set to 1. This state variable is used to stop the contract. We also implement this code inside a contract called circuit breaker, which also comes from the lib. So say circuit breaker, lib circuit breaker, and then say pot is circuit breaker. Okay, and now we can remove this state variable called live, and then also remove it from here. And then I noticed that it's checking that live is equal to 1. Going back to the circuit breaker, we renamed this modifier as not stopped. So I'll put a modifier called not stopped, and then we can remove this. Okay, and inside the constructor, I can also remove this wards a message sender equal to 1. This authorizes message sender. This is already implemented inside our contract auth. Okay, so next, let's rename the state variables. Pi will be a mapping from address to uint256. What this stores is the normalized DAI balance of the user identified by address. And what normalized balance of DAI means that whatever amount that the user deposited, divide that by the current rate accumulator, and that will be the normalized balance of DAI. Why would they store this? Well, it's part of the algorithm to correctly calculate the fee for all users that deposit into the pot contract. I've already covered how the algorithm works in a video about stability fees, so I'll put the link to the video in the descriptions. Okay, moving on. Next, we have another state variable called pi. It is with a capital P. This will be the total normalized balance of DAI. In analogy to ERC20, pi will be like balance of, and pi with a capital P will be like total supply. So let's rename this to total pi. Next, we have a variable called DSR. This is the DAI savings rate. Let's rename this as savings rate. Okay, and then next we have a state variable called chi, which will be the rate accumulator. Let's rename this as rate ACC, rate accumulator. And then we have the back contract. Let's rename this as CDP engine. And then we have the bow contract. Let's rename this as DS engine. DS will stand for debt surplus engine. Okay, and the last state variable we have is called row. This will be the time of the last drip. The function drip will be called to update the rate accumulator. So let's rename this as updated at. Okay, let's move on to the constructor. Takes in a single input, VAT contract. Let's rename this as CDP engine. And then it sets DSR in Chi to 1. DSR we renamed it as savings rate. Chi will be the rate accumulator, rate ACC. And what is 1? 1 is 10 to the 27. This will be rate. So let's import the math library. Import from div math.sol. The math library will contain all of the math code that we need, including the constants wad, ray, and rad. Okay, moving on. Row, we rename this as updated at. Now will be block.timestamp. Okay, and then next we have some math functions. This code is all moved inside the library called math.sol, so we don't need this. Okay, and then we move on to the administration function file. Let's rename this as set. And then for the key what, we'll rename this as key. And then data, we'll keep it the same. So let's see what's going on here. Require that now will be block.timestamp. Block.timestamp is equal to updated at. So it requires that updated at is equal to the current timestamp. And if the key is equal to DSR, let's rename this to savings rate. Then set savings rate to the data that was passed. And why do we require that the updated at, the last time that the function drip was called, is exactly equal to the current timestamp? The function drip will update the rate accumulator, and when the function is called, it will update this state variable called updated at to the current timestamp. If this check wasn't here, then we'll be able to change the savings rate without updating the rate accumulator. And if we don't update the rate accumulator, then this means that we didn't claim the DAI that we could have if we call the function drip. So this is why it requires that updated at is equal to the current timestamp. Okay, moving on. The other function set is called to set the bow contract. The bow contract, we name this as DS engine. Okay, so that completes the function set. Next, we have the function cage. The function to set the state variable live to 0. In our case, this will be handled by an internal function called stop inside the circuit breaker contract. So what we need to do here is call the internal function called stop inherited by the circuit breaker. And we also need to set DSR to 1. DSR will be the savings rate, and this will be set to rate. I forgot to set the savings rate for the constructor to ray as well, so I'll do that now, ray, and then ray over here. So that completes the function cage. Let's actually rename this function cage to stop. It's gonna stop the contract. Okay, and then moving on, we have the function called drip. What this function will do is it will update the rate accumulator, and whatever interest that it has earned from the last time the function drip was called, it will ask the back contract to mint that amount, send that amount to this contract, and send the debt, the on-back debt that was created, to the bow contract. Let's rename this function to collect stability fee. It's going to collect the stability fee. Okay, first it checks that current timestamp, block.timestamp, is greater than or equal to row. Row will be the state variable updated at. And you can see over here that the state variable updated at is updated to the current timestamp, block.timestamp, at the end of this function. Next, it does some calculation and then stores it in a variable called temp. It's a little bit confusing. So what I'm gonna do here is remove it and then say return temp, and let's redeclare this as uint256. So what is this actually doing? Well, let's spread it out to see what's going on. Let's start with the inner part, rPower. We rename this function as math.rPower. What this rPower function will do is divide x by b, the base, and then raise it to the nth power, and then multiply by the base again. In our case, this base will be ray, x DSR will be savings rate, now will be block.timestamp, and updated at will be updated at. So it takes savings rate, and then take the savings rate to the nth power, which is the difference in time from the last time it was updated in seconds, and then the unit that will be returned will be in rate. Okay, so that's the inner part. How about this part, rmul? This will be math.rmul, and then multiply by chi. Chi will be rate accumulator. Okay, so we now understand what's going on here. It's calculating the rate accumulated since the last time the function drip was called, and then multiplying it to the current rate accumulator. So this will be the new rate accumulator. Let's call this ACC. Okay, and then moving on, the next state variable is chi with underscore. And what it's doing is subtracting temp with chi. Temp will be the new rate accumulator, chi will be the old rate accumulator, rate ACC. So this chi over here will represent delta rate ACC. Okay, so let's rename all occurrence of this chi followed by an underscore with delta rate ACC. And then it sets the chi. Chi will be rate accumulator, the state variable. Temp will be the new rate accumulator. Call the function bat.suck. Here we renamed it as cdp engine.mint to address of the DS engine, DS engine. This will be the debt destination. The coin destination will be to this contract, and then multiply pi. Pi will be total pi by delta rate accumulator. When you multiply the total pi by the old rate accumulator, you'll get the old total amount of DAI that this contract earned. And doing the same thing, when we multiply total pi by the new rate accumulator, you'll get the current total amount of DAI that this contract earned. When we take the difference, we'll have total pi multiplied by the new rate accumulator minus the old rate accumulator, and this will give us the amount of DAI to mint. The difference between the old total DAI and the new total DAI will be the amount of DAI to mint. So that is what's going on over here. And then lastly, it returns a variable called temp. We rename this as the new rate accumulator, ACC. Okay, so that's the function drip. It collects stability fee from the CDP engine. Okay, moving on, we have two more functions, join and exit. Join is called by the user when they deposit their DAI into the pot contract, and exit is called when the user wants to withdraw their DAI from the pot contract. Okay, let's start with the function join. Now will be block.timestamp and row will be updated at. First, it checks that the state variable updated at is equal to the current timestamp, which means that before anyone can call the function join, they must have called the function drip. In our case, this is collect stability fee. The reason why this check is needed is to make sure that whatever amount of DAI that the pot contract earned, it first claims it before it allows anyone else to deposit. If this check wasn't here, then this will allow the depositor to earn some DAI that they should not have claimed. Okay, next it updates the mapping called pi for message sender by adding the current pi for the message sender with wed. Let's refactor this and say plus equals wed. And then we'll do the same for pi. We rename pi as total pi. And then we'll use plus equals wed. And then it calls the function bat.move. Bat will be CDP engine, move will be transfer coin. So what this call is doing is transfer coin from message sender into this contract for the amount chi multiplied by wed. Let's replace this with chi multiplied by wed. And chi, we renamed it as rate ACC. When we multiply rate ACC by this amount wed will be the normalized DAI balance that the user deposited. And since over here it's calling CDP engine, transfer coin from message sender to this contract, before the user calls the function join, they must first transfer DAI into the CDP engine. Once the DAI is transferred over to the CDP engine, they will be able to call the function transfer coin to move the coin from their account over to this contract. Here it's multiplying by rate accumulator times wed, so this wed will be the normalized DAI balance. Okay, so this is the function join. let's finish up with the last function, exit. First thing it does is subtract from the current balance of pi. Again, this WAD will be the normalized balance. And then we'll rename this as total pi, and then subtract from total pi, and then call bat.move. Transfer coin from CDP engine, and the amount will be transferred from this contract over to message sender for the amount chi multiplied by WAD, or rate accumulator multiplied by WAD. By multiplying the current rate accumulator by WAD, this will calculate the correct amount of DAI that message sender has earned. And notice, for the function join, it checks that the last time that updated was called is equal to the current timestamp. However, this check is not included in the function exit. The reason is, message sender will only lose if they don't call the function drip before calling the function exit, because the total DAI that this POC contract earned is only claimed when the function drip is called. And when the drip function is called, the state variable updated at is updated. If they don't call the function drip and they call the function exit, they're just missing out on the DAI that they did not claim. Okay, so that completes the POC contract. Let's try compiling the contract. Inside my terminal, I'll type forge build. Okay, so I see some errors on line 43. Okay, I'll rename this as CDP engine. Next on line 92. Okay, let's try compiling again. Okay, I can remove the public keyword from the constructor. Okay, and our contract compiled.